assuming they don't put you to sleep. Okay, and so right off the bat, they're talking about a Walsh diagram, but a Walsh diagram has everything to do with symmetry, and everything to do with symmetry is chapter 15, so there's really not a whole lot of point to talk about the Walsh diagram. And it's just saying that if you have the same symmetry, those lines can't cross, so I wouldn't even really worry about the Walsh diagram.
So it's not going to be on our test.
I wouldn't worry about it. Right? Okay, but just showing how orbital energies change as you change. What are they changing anyway? I feel like they're changing angle, right? So as you change these orbital, I don't see how they're changing orbital energy. Maybe they're changing the energies that goes up. I just know that if you have the same symmetry, those lines can't cross. But that's DWA. Don't worry about this Walsh diagram. I shouldn't even have it on there. Non-bonding orbital. So we're talking about those molecular orbitals. We take a bunch of atoms from the molecule, right? We combine the atomic orbitals and we get molecular orbitals. Well, if these molecular orbitals are lower in energy than atomic orbitals, they'll be what type? Bonding. And if they're higher in energy than the constituent atomic orbitals, they'll be anti-bonding. But what if they're right at the energy of the constituent atomic orbitals? Non-bonding. Okay.
What's non-bonding? When they're lined up with each other.
Yeah, kind of like, here's the atomic orbital energy level.
Oh, yeah.
And then, okay, well, here's my molecular orbitals over here, but hey, that's the same energy. So that'd be non-bonding.
High in energy is anti-bonding, and bonding is low in energy.
So remember from organic chemistry, these conjugated molecules. What's a common conjugated molecule you've heard of? Usually you hear the word aromatic, but benzene, right? You have these delocalized electrons, right? This is getting into, I think this is getting into Spartan, and all the little check boxes you could pick to do the calculations on Spartan. And one of those is a Huckel box, and I don't even know if you have that box to pick, because you probably don't, because the computers are getting so good now they don't need to set everything to 0. You remember we had this symbol S for overlap integrals for different different molecular orbitals and seeing how they overlap. Well, the Huckel approximation just sets all overlap integrals to 0. So even though they're not 0, so it's kind of, I don't even, well, that's what it is. These frontier orbitals, we're going to have a whole pile of molecular orbitals. Pretty much we're going to start talking about solids instead of take a bunch of these molecules and combine them, and you start getting this big continuum of orbitals. And then, well, at some point though, the electrons always fill up from the lowest energy to the highest. At some point they get full, right? You reach the top of it. Now, but that means above it, these molecular orbitals are empty. So you with me so far? So you start with, this is what's coming up. You're going to have a solid, and they're going to say, hey, each atom here is donating in an orbital. Great. So if I have n atoms, I have n orbitals. Well, that means I have so many electrons. Electrons fill up the orbitals, lowest to highest. At room, make it really, really cold, so lowest to highest, there's no excited ones, and they're full at some point. Well, do you remember this talk? I think you've used this talk. HOMO and LUMO, that would be your lowest energy transition. They call those the frontier orbitals, right? HOMO is highest occupied molecular orbital. LUMO,
lowest unoccupied.
Yeah, molecular orbital. Yeah, you know all that. Okay. So there's some of those funky names in Spartan where you could have the calculations done this way, and they're called semi-empirical. And this will be a lot faster than if you click the button that's an ab initio. Because semi-empirical cheats. It knows that you're trying to do something with the benzene molecule. And first it has to know that it's benzene. And then it uses the ion, for example, some empirical data, like experimental data. Ionization energies are really the most common. So it's going to use ionization energies in the calculations to start right off the bat writing better wave functions and to get the whatever you're after. It could be vibrational modes or whatever. So it's faster because it's kind of cheating. You're using experimental data. Ab initio, slower because there's no experimental data in there whatsoever. It's from pure theory is where they're doing all their calculations. Here, if you have differential, if you have different atoms, wasn't it? Just different nuclei, it ignores the overlap. So there isn't really a whole, again, this kind of stuff, no, there's not really much really to ask. I mean, this is really specific, kind of dealing with Spartan. Gaussian, this is how they like to write it. So they use that in the ab initio methods. So here's a little more conceptual stuff that I think you can see on the exam. This would be more, if you see what's going on here. They're trying to say that, okay, this side is the individual atom. This side is the solid. So solids are made up of atoms. So they're talking about these atomic solids. Do you remember from general chemistry, we had all these different types of solids we talked about. We talked about metallic solids. We talked about molecular solids. You remember this? And we're going to get into semiconductors and insulators, and you've probably talked about this before, but the point is on this side, here's the energy of the orbital that atom's donating, right? What's its highest, the highest energy orbital that it's going to donate, right? Where are these electrons at, right? We're not worried about the closed shells, but we're interested in the valence electrons. So what's the energy of these orbitals? So that's this side of that atom. Because remember, it's a solid. It's all the same atom, so they're all going to have the exact same energy. Okay. Then each one of these atoms, they get a gazillion atoms, right? They're each donating an orbital. This is what you end up with. This side. You get a smear of these orbitals. It's like a continuum, right? It essentially is a continuum. There's no energy levels here anymore. It's just top and bottom of this whole smear, right? Like a band, would be the best word. Here I see an energy level, but here I just see a big smear, a big band. Okay, so what they're trying to say is, okay, at the bottom, bonding or anti-bonding, or non-bonding? Bonding. Up here, higher than the constituent atomic orbitals? Anti-bonding. Right straight across? Non-bonding. Okay, so, and they're trying to show how you generate that band. Well, one atom, nothing really changed. Two atoms, anti-bonding, bonding. Three, now you introduced non-bonding. But come on, you don't have a solid with 3 atoms. You need a gazillion atoms. So that's where you end up with. Okay, so with this idea, and then however many electrons you have, right, they'd fill in there. With this idea, how do they explain metallic conductors? Because what's filling up these orbitals? Electrons. So how do they explain metallic, with this theory, band theory of solids, how do they explain metallic conductors? It's kind of simple in the sense that just don't shade this whole thing in, right? Let's say my highest occupied molecular level is right here somewhere. I don't know. So I'll darken in everywhere where there's electrons, right, that are full. Are these molecular orbitals just is the HOMO very close to the LUMO? It's a band, right? I mean, it's essentially right next to it. It can jump up there. Well, there now it's conducting. It's free. It's in the conduction band. So they kind of call that the conduction band, right? Is there any gap between this HOMO and LUMO in a metal? No, that's the idea with a metal. There's no gap between the HOMO and the LUMO. It's just right there. It's a band. It's a solid. It's a solid smear of orbitals. So if there's no gap, well, yeah, this is a metal. It's going to conduct really easily. Hey, if you heat it up, what happens to that conduction? Is it easier or tougher?
Tougher.
It's tougher. Why? Why does the resistance go up with a metal? Because at first glance, for me, I look at this, and that's the right answer. But I was hoping you'd say something else, because for me, logic says, man, I give this some energy, heat, fine, and this seems to fit perfect. So these levels, these molecular orbitals, they're right next to one another. It's a band. You can't even distinguish between them, right? So give it a little heat, they're going to jump up into that conduction band and whoosh, right? Man, if things go whoosh, that's conducting even better, right? Whoosh. But that's not what happens. These electrons, yeah, they get kicked up there really easily, but I think what they say is that you get too many of them. And electrons that each have all the same charge. One's trying to go this way, one's trying to go this way. Well, now and if you want to get current, you need to go from location A to location B. That's a set direction. But if you have all these electrons up there, they're all repelling each other. Well, I want to go from A to B. You're making it more difficult to go from A to B because you have things in the way. I think that's what it is. So if you make things colder, so there's less electrons, yeah, the resistance will go down because you don't have as much stuff in the way. So there's not that much chaotic motion at that sea of electron thing that I'm trying to imagine and getting from point A to point B, because that's what charge is. That's what current is. It's a moving charge. So that's the idea behind a metal conductor. Okay, so then if that's what a metal conductor is, what would be well, let's just do this one in order. Semiconductor. Right?
There's a gap in between.
Yeah, a gap. Right. But a gap between the what and the what? HOMO and LUMO. Right? Is it a huge gap? No. Yeah. Because if it was a huge gap, if you can't jump across there, it would be an insulator. Exactly. Okay. So with metals, you increase the temp, and it got more resistive. With semiconductors, increase the temp, what happens to resistivity? Increase the temp. So that gap, that band gap has to be pretty dang small because you want just heat to allow electrons to jump that band gap. Right? Add some heat, electrons jump the band gap, and there's not very many of them. Only a few get up there. So man, there's not much chaotic motion there. They can go from point A to B pretty dang easily. So if you increase the temp on a semiconductor, the resistance goes down, right? It's going to conduct, conductivity goes up. It's a lot easier to conduct electricity. But they like to talk about resistance for some reason with this sort of stuff. So you have to talk about resistance. So semiconductors, if you heat it up, darn, resistivity goes down. When, man, see you guys walk around with all these cell phones and gazillions of encyclopedias in your pocket. It was only what? How old am I? That was like 20-some years ago. You walk into the room, and it's frigid. All these computer science people had it made 20-some years ago because all their rooms were frigid. You know, if you like air conditioning. Kevin would have loved this. right? Why were all their rooms cold? Because of the computers. There were some real issues here. Remember semiconductors? If the temperature got warm, the resistivity drops and things just burned out and they destroyed all their $1 million computers. Well, $100,000 computer, whatever, right? But now we've fixed those issues, and we'll probably get into that, but so we don't have to worry about that so much anymore. So we called these, what do we call these again? Start with a B. Bands. We call them bands. So, and how do we generate them? Each atom in the solid essentially, theoretically, donates an atomic orbital. Okay. If that atomic orbital is an s orbital, then we'll call it a what band? S band. If that atomic orbital is, from the 2p, from the 3p, we would call it a p band. So that's this stuff. Okay, we kind of defined band gap already. Here they're trying to show you what, at the top, anti-bonding, right? Remember what the different colors meant?
Signs.
Different signs, yeah. So a lot of destructive interference there. So there's nodes galore. It's anti-bonding, pure anti-bonding.
Different signs, like plus or negative.
Plus minus of the wave function, right? Of the wave function. And then down here you have pure constructive interference, so pure bonding. So in between is just a mess in between, right? So whether it's in s orbitals or here you have these p orbitals. Okay. So one thing you can do, I don't know if you want to mess with that. There's chemical potential right there. I don't know if you really want to worry about this. At 0.5, that's where it's I don't think we're going to worry about that. Let's not worry about that. Since we're talking about these bands, let's talk about dopants, right? If we can mess with these. I know it's flipped. I noticed that. So I flipped it around. So don't even worry about it. If we can mess with this Fermi level. What's the Fermi level? According to this picture, it looks like what?
Like the border between the luma and the HOMO?
Yeah. Where's it at? Right, exactly. So we can mess with it. You can get more electrons in that solid and mess with that Fermi level. It's going to, if it didn't look like this, like a metal, it would look, you're starting to mess with properties over here. You're really messing with electric properties. If you can mess with that Fermi level, bring it up and down, how do they do that? And that's how they fix this whole issue of you don't have to have super cold rooms anymore. How do they do that? What's a dopant? Right? I almost need a periodic table here. Yeah, I'll find a periodic table. And we can talk about dopants. Okay, where's a semiconductor? Where's a semiconductor, Gloriana?
Over here?
Yeah, somewhere over here. Germanium. Fine. Okay. Germanium has 4 valence electrons, right? 2p, 3p, 4p, make a p band. Okay. What if, so you've got this crystal of germanium. And it'd be really cool to know how they do this, right? Probably just by diluting it and adding things, but arsenic has 5 valence electrons. So replace a few of the germanium atoms with arsenic in that crystal, right? And exactly how they do it, I'm sure they don't pop and put it in. I'm sure they just get the whole thing to vaporize or melt and get a nice homogeneous mixture and make your solid. But I'd be interested to see how they do that. But the point is replace, have has some arsenic in that crystal. Well, now my Fermi level is going to go what? Can you see the periodic table? You had germanium. I have a few atoms of arsenic in there. Now the Fermi level is going to go have more electrons. It's going to go up, right? So here it doesn't look like it does much, right? But if you start looking at a picture like this, going up a little bit can really change the conductivity of it, okay? But you could go the other route. You could, okay, replace it with some gallium. Now you've got less electrons. They call those holes. So in that one spot where that gallium is, it can conduct because there's an open molecular orbital there. You're generating holes. So you can, that's why they call this N-type and, I think it was N-type and P-type. Yeah, N-type and P-type. N for negative, P for positive. So you can dope with atoms that have more electrons than the semiconductor material, or dope with atoms that have less. Okay, you make that as complicated as you want. I mean, that was very simple. They make it much more, you can go a lot further with that than what we're talking about. So
dopant is just something that has electrons on it?
yeah, dopant is going to be modifying the chemical nature of that solid. So you remember, you want to start with this pure solid in the first place. Okay. And then just by giving it impurities, making it impure, it sounds better to dope. Because if you say the word impure, you're making it sound like you don't know what you're doing, right? So they're going to say dopant. We're doping it. Really, you're just making it impure. Does that make sense? Okay. And you'll see that the homework here isn't a whole lot. I mean, look, you only have 2 questions. So we'll get this homework done, and then you can enjoy your weekend. I think you can, because there's not a whole lot to study. Yes, you will. Go see the shroud.
Go see the what?
Isn't it, what is it? It's here till the end of March?
Something like that.
What's that?
It's very scientific. Whether you're a believer in the Bible or not, man, there's a lot of science there. It's really interesting. And history, if you're a history buff. Okay, just Google it, Gloriana. You'll see what it is.
What is it called?
Shroud of Turin. S-H-R-O-U-D of Turin. T-U-R-I-N. It's going to cost you $10 though.
Okay. I think I have $10.
Okay, give the parities of the 6. Okay, give the parities of the 6 pi molecular orbitals of benzene. Isn't there a hint for this?
Yes. Use figure 14.
Yeah, because I don't know what the heck the pi molecular orbitals are of benzene. Because we just have a table for those diatomic homonuclear molecules, right? So if they want to talk about benzene, well, someone's got to do all the Spartan calculations and give them to us. So we need to find the table.
14 what?
Oh, you got a book. Wrote them down somewhere. What does it say on that page?
You got it right here. Wait, this page? Oh, that one? No, I don't got it. Never mind.
You don't have it.
I don't got it. I don't have it.
What page are you on, Mel?
Yeah, 416.
Page 416. And we're supposed to give the what?
The U or the G?
There. If you recognize that, this is easy. Parity is U or G. Exactly. So to have a U or G in the first place, oh, here's a good question to see if you're ready for the exam. If you have a U or G on these molecular orbitals, that means that molecule has to have a what?
Inverse
center of inversion, or inversion point, whatever you want to call it. Right? That little I symbol, that symmetry operation where you can transpose from one side to the other side of that molecule and get the exact same thing. And benzene you can. Benzene has a center of inversion. So all of benzene's molecular orbitals had better have a G or U on it. So you look at that page, 416, and you just pretty much write down whether it's G or U, and you're done. I mean, how easy can this get? There it is. Right?
You're gonna share the book with us?
Gloriana can share. That's the kind of person she is. So that's 5. 12. 12 has hint. Use figure.
Nobody gets it. Nobody understands. I don't get it either.
Oh, you're talking about 5 still, not.
Yeah.
Okay, so notice there aren't any pi's and sigmas anymore. We have little a. See, there's a B, E, E. Now this A, E's, and B's and stuff, it's going to make a lot more sense in chapter 15. So we just got to suck it up and live with it. All we're looking at is parity. And parity is exactly what Kevin said, G or U. So the molecular orbital A2U, its parity is U. Now you could even be more technical and give it the actual name, Ungerada or something, right? Yeah, I'm not very good at German, so yeah. So that's all you do. So how many answers do you have? A2U is of parity U. E1G is of parity
G.
Gerada. Yeah.
There's not an overall parity?
No, each molecular orbital has its own parity. And you can kind of tell by looking at it, right? Because see how they sketched it out? And if it's Gerada, let's see, if it's Gerada, right?
B2G.
Because there's 6. Do we have 6? 1, 2, 3, 4. Yeah.
Oh, yeah, we do.
1, 2, 3, 4, 5, 6. Because there's E2U has 2 and E's have 2.
What was the next one? E2G?
E2U, E1G, A2U. B2G, E2U, E1G, A2U.
Wait. I was going from the bottom to the top.
The bottom, A2U,
Yeah?
E1G,
Oh, E1G. You told me E2U.
that's your next one. She was going in a different order.
Well, it doesn't look right, though.
Yeah, I know.
Because if you look at these things, if this is Gerada, you should reflect through there and you should get the same sign. Right? Doesn't make sense.
Reflect through what?
Right? Because here the center inversion is always in the center of all these molecular orbitals, these weird looking things. That doesn't make sense. Because A2U is Gerada. Look at that. It's the same sign everywhere. See what I'm saying? Because you reflect through here, if you call light positive of the wave function, if you go from positive to positive no matter how you reflect through the center. If you reflect through the center on E1G, what do you get?
Negative.
You always get a negative. Or a negative goes to a positive. So E1G should be Ungerada. U.
Ungerada.
Just say U. Just say
Okay,
U. E2U should be,
Ungerada. Right?
you see Ungerada on E2U? I see Gerada. Don't you get the same sign no matter how you reflect through it? Kevin, get off your butt and look at this.
I don't think so.
I see different colors.
Yeah, I see different colors.
You do?
too.
Well, use your piece of paper here. Reflect through it. No matter how you reflect through it, you have to reflect through the center, because the center inversion is right there.
What if you go like this? And that's different.
Yeah, but there's nothing and nothing. So pretty much anywhere else besides what you're talking about. C++, minus, minus.
Okay.
And same thing over here. Plus, 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 minus, minus. So this should be Grata. How about this one? U. Yeah, because you have to go through the center, though. I think that's U.
So it's just like opposite of what the letter is.
Yeah, what the heck? Doesn't make any sense.
Just change the
That's
letters.
easy.
Yeah. Yeah, so change those letters. Does that make sense? So to answer a question like this, I would have to give you the molecular orbitals, and then you just look at them and see what if the wave function changes sign or not. Okay? So we don't give their parities on their molecular orbitals. That's messed up. Grata,
Ungrata.
Ungrata, Grata, and Ungrata. Yeah. I don't know what's going on there. That's weird. Predict the electron configurations of the benzene anion, the benzene cation. And they said, they gave us a hint here too. Where's figure 14.44?
That one.
Oh, it's the same one. Okay. So they're saying, how many electrons are they giving benzene here?
2.
'Cause how many arrows do you count in this? Because here's the entire diagram.
6.
6. So they're saying benzene has 6 electrons to work with. Okay, 6 valence electrons. So if you want a benzene anion, now you don't have 6 anymore. You're going to have
6, 7, 8 electrons.
I know, but they're just saying there's 6, so that's what I'm working with. Because they said this is benzene. So if you wanted to write, before you even do an A prime, how would you write the electron configuration of benzene according to this molecular orbital table? How would you write the electron configuration of benzene? A2U with a little superscript 2, and then with a superscript 4. Exactly. A2U with a little superscript 2, E1G with a little superscript 4. They didn't ask for that, though. They should have. That would have been kind of nice. It gave us a starting point, but they didn't. So instead, they want you to write the electron configuration of the benzene anion. So you would write
Jump one up. E2U1.
Wait. Oh, I see. I get it now.
now if you want an anion, are they talking about promoting one of these up there?
No, you're getting another.
No, you have to have a whole nother electron. So where does it go? Is E1G full?
No.
Is it?
Yes.
Yeah, E1G's done.
It is
Right?
full.
So, because there's only 2 there, so you have to jump up at E2U. So, A2U2, E1G4, E2U.
Oh, E1G4. I get it now. This one's A2U2
Yeah. Yeah, you make sure there's superscripts.
and E2U1. Is it 1?
Mm-hmm. For the anion. For the cation, you'd write what? Mm-hmm. And then when they start talking about, now you have to pretty much read the what do you call this? The text to answer the rest of this. Well, maybe even to answer what we just did would have helped to read the text. But estimate the pi bond energy in each case. So you have to look through here and see what is they're saying that there's energy in each one of these. So what is that energy? And what I did is I'm looking at their text and see how they have, you see right here, they have 2 in the A2U, they have 4 in the E1G. If you look straight over here, the pi electron bond energy of benzene is. So 2 times something, 4 times something. So that means this, alpha plus 2 beta, has to be the energy of this guy, right? Because they just said 2 times it. And then they said 4 times something, so that alpha plus beta must be this one. Okay? And if you keep looking in the reading, this one's alpha minus beta, and this one, I don't even know what that other one is. Right? Somehow I found out in the reading this one's alpha minus beta.
You don't memorize that, do you?
It's out of here.
Okay.
So I'd have to be giving you this information somehow, right, if this was on the exam. So how do you figure out these energies? Do the same thing they did for the ground state of benzene. They said 2 times. So you look at the number of electrons, and then you multiply it by the corresponding alpha beta expression. Then it's pi energy. Right? It's pi electron energy. So for each electron configuration that you wrote, right, I think we wrote a cation. So it's going to look very similar to this, except the 4 will be a 3.
Oh.
And then for the anion, you're going to have, it's going to look just like this, but you have an extra term. It's going to be 1 times this alpha minus beta. And how I figured out that's alpha minus beta, I'm not sure where that is. Probably here.
Is it plus always? Like between the operation?
Yeah, it's going to always be plus. So they're going to give you an alpha beta expression for each one of these molecular orbitals. And you always you're adding them up. And you multiply that alpha beta expression times the number of electrons that have that are in that molecular orbital.
Wait, how did you get for the second one? For the cation?
Cation, you have to take one away. So
Right.
so your configuration was a 2 and a 3 electrons.
Right.
So 2 times this guy plus 3 times this one. And this one was alpha plus beta. This one was alpha plus 2 beta.
So it's just like the 2
Yeah, it's
would
gonna
be here, and then this
one.
one.
You said there's 3 electrons.
Oh, but this one would have a 2 there, and then this
Well,
one
you
would
didn't
have
change
a
him,
3.
did you?
No.
No, so leave him
So
alone.
This one I would have a 3 though.
Yes.
They all
Okay.
equal the same thing?
No. Right? It'd be different.
Yeah.
Like for the first one, it'd be like
Oh,
5
because it was
alpha plus 6 beta. Whoa there. Be- right. 5 alpha plus 6 beta.
I wouldn't.
I hear you, but
That's for the first one.
3.
But wouldn't it be 4? Because we wrote 4 for the first one.
Oh, did I get
This
that
one we
mixed up?
wrote 3. The anion is 4. Right? Because that's why he said we had to do this one. Because remember we
Oh,
went
yeah,
to
yeah,
the-
yeah. Yeah. So this is, so I just switched them?
Yeah, so then we would do plus alpha minus beta.
For which one?
Because it would be like 2 times alpha plus 2 beta.
So these are
plus
alpha minus 7
4
beta.
alpha
Plus
beta.
7
Wait,
beta.
say that again.
Plus.
To be 2.
For the anion,
2 times alpha
Yeah,
plus
plus
2 beta,
7.
right?
plus 7 beta.
Yeah,
Plus
plus
Oh,
seven
yeah.
beta.
Plus
And this
4 times alpha plus beta.
plus alpha minus beta, wouldn't it?
Yeah.
Then for the cation, you got what?
5 alpha plus 6 beta.
5 alpha plus
5 beta? Oh, sorry, 4, 5, 6, 7.
7 beta.
5
Oh,
alpha.
7 beta.
You said you got the alpha